In this video, we're going to focus on density exercises. So as a quick review, density is equal to mass over volume. And the units for density typically are going to be grams over centimeter cubed or grams over milliliter, where 1 milliliter and 1 centimeter cubed are interchangeable. But that's typically going to be for solids and liquids. Now gases, because they are less dense than the solids and liquids, you will typically see those in grams per liter. Okay, again, you'll have the same amount of mass spread over a much larger volume because it is less dense. So in our first example, the density of water is approximately 1 gram per centimeter cubed. Now we need to remember that that is the same thing as 1 gram per milliliter. Which of these objects will float on water? Okay, so the way that this question, or what this question is asking, is which object is less dense than water? So when we're talking about something that floats, it needs to be less dense than the liquid that it is in. Okay, so iron, because it has a larger density compared to water, it's not going to float, it's going to sink. And the same for gold. Again, much larger density compared to water, and so that will sink as well. But ethanol and olive oil both have densities less than 1, and so those two are going to float. All right, so when you're asking about floating or sinking, you're just asking about less dense or more dense compared to the liquid that it's in. Okay, next example, we've got calculate the density of aluminum given 27.6 centimeters cubed. So because of the centimeters cubed, that is your volume, right? Because those are units of volume, and mass of 74.6 grams. Okay, so remember that density is equal to mass over the volume. And therefore we can plug in that mass of 74.6 grams divided by a volume of 27.6 centimeters cubed. Okay, and in terms of significant figures, you've got 3 sig figs in the top and the bottom number. So our final answer is going to come out to be 2.70 grams per centimeter cubed. Now don't worry if you haven't covered sig figs yet in your class. I'm sure that that will come soon. But we typically want the least number of digits in our answer of the numbers that we use in our calculation, if it's multiplication and division. Okay, the next example, we've got a large piece of jewelry has a mass of 132.6 grams. A graduated cylinder initially contains 48.6 milliliters of water. When the jewelry is submerged in the graduated cylinder, the total volume increases to 61.2 milliliters. So sometimes it can help to draw a picture where we have this container. Technically it's a graduated cylinder, so it may look a little bit taller and skinnier than what my picture has. But it initially contains so much water. Okay, and that water level is right at 48.6 milliliters. Okay, and then we're going to add to this graduated cylinder a piece of jewelry. And that's going to raise the volume of the graduated cylinder to a new height of 61.2 milliliters. Okay, so if we want to determine the density of this piece of jewelry, we need to know the mass, which they give us, as 132.6 grams. Okay, and we also need the volume of the jewelry. And the way we have to determine that is what we call volume by displacement. So, to determine the volume of the jewelry, we're going to want to take the final volume of the liquid, that's your 61.2 milliliters, and subtract the original volume of the liquid to see how much was changed when we added the piece of jewelry. Okay, when we are adding and subtracting, we want our final answer to be reported to the same decimal place as the shortest decimal place in the numbers that we use, which is the tenths place in this case. So we should get back 12.6 milliliters for the volume of the jewelry. And once we have that, we can then calculate the density, which is equal to the mass, 132.6 grams, divided by the volume of the jewelry, which is that 12.6 milliliters. Okay. And our final answer, again, we want the least number of digits, which from the volume is 3. So we get 10.5 grams per milliliter. Notice how none of the units cancel out when we're calculating density. We have to keep the gram and the milliliter. Okay, next example. We've got a solution is made by dissolving 15 grams of a salt in 200 centimeters of water, where the density is equal to 1 gram per centimeter cubed. And there they are talking about the density of water. Assuming the volume does not change, what is the density of the solution? Okay, so sometimes when I see that there are multiple substances like salt, water, and solution, it is good for me to use subscripts so that I know that I am looking for the density of the solution. Okay, so that means that I have to have the mass of the solution divided by the volume of the solution. Okay, now they give me the mass of the salt and the volume of water, but they do not give me the mass of the solution. But they give me the density of water so that I can figure out how much the mass of water is. So remember that solution is going to be equal to the total of everything involved in that solution. In this case, it's going to be the salt plus the water. So if I want to find the mass of the solution, I need to find both the mass of the salt and the mass of the water. Okay. Now, since the volume of the water is 200 centimeters cubed, and we know the density is 1 gram per centimeter cubed, then if the volume is 200 centimeters cubed, the mass of the water is 200 grams. Okay, and we can get that by taking the volume and multiplying it by a density of 1 gram per centimeter cubed. Okay, so those centimeters cubed cancel out. That's just showing you how I got to it. But the mass and the water are the same, just with different units. And that's the mass of the water. Okay, so the mass of the solution is then going to be equal to the 15 grams that you have of salt plus the 200 grams of water. So the mass of the solution is 215 grams. Okay, so I have the mass. And then it says, assume the volume does not change. So what they're saying is that the volume of the salt, of those 15 grams of salt, is so small because it is a solid and it's densely packed that we're going to assume that the volume of the solution is equal to the volume of the water, which is that 200 centimeters cubed. Okay. So to find the density of solution, that's going to be equal to the mass of the solution, remember it's the total mass, 215 grams, divided by the volume of the solution, which is the same as the volume of the water, and that's 200 centimeters cubed. So if we were to assume that those zeros are significant, and that's exactly 200, we should get back three digits of significance, which is 1.08 grams per centimeter cubed. But if you were to assume that that 200 only had one significant figure, okay, then you may have to round this to 1 gram per centimeter cubed. But I'm going to assume that they meant the 200 was 3 sig figs and that that is 1.08 grams per centimeter cubed. Okay, last example. Consider the following scenarios and determine which object has the larger density. Okay, so these are conceptual questions. We've got two objects with the same volume, but one has a larger mass. Okay, so if we assume that density 1, and we'll look at density 2 of each one of the objects. So they have the same volume. Okay, so whatever the density of 1 and 2 are, those volumes are identical. But one has a larger mass. So let's say that density 2 has a larger mass. Compared to density 1. So because mass is on the top of the fraction, if we increase the mass, we are going to increase the density as well if volume is held constant. Okay, because volume is underneath the fraction, it's going to have an opposite effect. So mass is what we call directly related, and volume is indirectly related. Okay, so mass is directly related, which means that if the mass goes up, so will the density. And therefore, the one that has the larger mass is going to have the larger density. Now in the second one, we've got two objects with the same mass, but one has a larger volume. So this time, the mass of the first object is identical to the mass of the second object, and what we're changing is the volume. And so again, let's assume that the density of object 2 is the one that has the larger volume. And so because it's on the bottom of the fraction, if volume goes up, density will actually go down. So the object that's going to have the larger density will be the one that has the smaller volume. Okay, and of course you can always test this out. You could put in values where mass is equal to 1 for both cases, and then divide by different volumes. So we could divide by 1/10 for density 1, and for the second one we could say that it's 1/100. And if you plug that in your calculator, you will see that 1/10 is greater than 1/100th, and so the smaller volume will have the larger density. And then the last example, two objects made of the same material, but one is larger in size. So the key word here is the same material. Remember that density is unique to the type of material that you have. So say if we have a piece of gold, it doesn't matter whether it's larger or smaller. The fact that it's gold means that it will always have the same density. Okay, so two objects made of the same material will have the same densities. Okay, so that's kind of a trick question. Okay, that wraps up this topic.